In solving our quadratic equations, often we came up with problems which required the use of complex numbers. Today we're going to take a look at complex numbers in detail. But to kind of set up what they are, I want to look at how mathematicians have worked throughout history real quick. We often have a need for new numbers. I want to emphasize these are not fake numbers. These are actual numbers in order to solve new problems. So the first example that comes along is when the Chinese were trying to solve problems like x plus 5 equals 2. They came up with this revolutionary idea that x is equal to negative 3. They came up with this revolutionary idea that centers around the idea of creating new numbers. They created negative numbers. And this opened up a whole new realm of possibilities of what math can do. Just take, for example, the weather outside in the middle of the winter is a negative number at times. A second example of this was in Egypt. The Egyptians were dealing with problems like x squared equals 7. Whoops. No, they weren't. The Egyptians weren't solving problems like that. They were solving problems like 3x equals 5. Sorry. And they came up with this crazy notion that x equals 5/3. Well, okay, I'm bending history a bit. They used what are called unit fractions, and if you want to know more about unit fractions in the Egyptians, you can Google that. But really, they pioneered this idea of creating these new numbers called fractions. And fractions opened up a whole new realm of possibilities of what mathematics could describe and be used for. So again, another useful breakthrough in the ancient history of mathematics. It was the Greeks that solved problems like x squared equals 7. And they came up with this crazy notion that x could equal technically plus or minus, but we're just going to go with the square root of 7 for now because the Greeks hadn't met the Chinese at that point and worked with negative numbers. They came up with this idea of the square root of 7 being not, which we cannot write as a fraction. We cannot write as a decimal. So they had to create irrational numbers. Numbers that could not be written as a fraction. Numbers such as pi, the square root of 2, and, in this example, the square root of 7. And there was one other major breakthrough in creating new numbers to make new problems possible to solve, describe, and model with mathematics, and that was the problem that if x squared equals negative 1. By taking the square root of both sides, we would find out that x is equal to the square root of negative 1, which isn't a real number. And so we defined it as a new number, I. And in doing so, we created what were called the complex numbers. Now I want to get a hold of a guy who called these imaginary numbers because it creates an illusion that these numbers are fake. The word imaginary numbers was used to be kind of the almost humorous opposite of the real numbers. Well, if they're not real numbers, they must be imaginary. But imaginary does not mean they're fake or some figmentation of some person's imagination. They're actually useful numbers that can be used to describe many things, such as current flow of an electrical circuit. Engineers use these type of problems. I is an actual number. It's just called imaginary. Terrible naming system. Math needs better PR. But, so to avoid this confusion, I'm going to call them complex numbers throughout this video. These complex numbers are actual numbers that are very useful, and we can do a lot of mathematics with them. In fact, most of mathematics looks exactly the same as it did before, with the only definition we need that I squared is equal to negative 1. Thus, really, I is representing the square root of negative 1. So now we can solve problems like the square root of negative 9, because we can split up the square root of negative 9 into negative 1 times 9. The square root of 9 is 3, and the square root of negative 1 is an I. So therefore, the square root of negative 9 is 3i. Number 2, square root of negative 5. We can even do things that don't come out pretty, because we can split this up to the square root of negative 1 times 5. And the square root of negative 1 is I, and the square root of 5 stays inside the radical, because we can't take its square root. We can also do negative the square root of negative 13. Well, we have negative the square root of, we'll take that negative out as a factor of negative 1 times 13. And then we have negative, the square root of negative 1 is I, and the square root of 13 is going to stay behind in the radical. Let's take a look at the example, the square root, or how about negative square root of negative 25. When we have the negative out front, square root, negative 25 becomes negative 1 times 25. And with a negative out front, the square root of negative 1 is I, and the square root of 25 is 5, and so we have negative 5i. We can even make this more interesting and do the square root of, actually let's just make it positive square root. We're going to do the square root of negative 18, which we can write as the negative square root of negative 1 times 18, but we can actually even break that 18 down. 18 is 6 times 3 and 3 times 2, so what we really have is the square root of negative 1 times 2 times 3 squared. And we can take the square root of negative 1, that's the I. We can't take the square root of 2, so it's going to stay in the radical, but the square root of 3 squared is just 3. And so the square root of negative 18 becomes 3i square root of 2. Now that's kind of how we can evaluate radicals using I to give us solutions of problems we could not solve before. In terms of manipulating and working with the i's, it's really going to be no different than anything we've seen before. If we are adding or subtracting complex numbers, we will treat the I like a variable. No different than any other variable such as x or y. So for example, if we had 4 plus 3i, a complex number, and we add to it 6 minus 7i, another complex number, a plus in the middle really isn't going to do anything. We can just combine like terms. 4 and 6 is 10. 3i minus 7i is negative 4i. And we have now added these complex numbers together. How about we try a subtraction problem? We'll take 2 plus 5i, a complex number, and we'll subtract 3 minus 6i, another complex number. Now this time the minus in between does make a difference, because it has to distribute through the entire parentheses. So let's do that. We have 2 plus 5i minus 3 plus 6i. Now when we combine like terms, the real parts, 2 minus 3 is negative 1. The complex part, 5i plus 6i, is 11i. And we have our solution. Probably two common errors come up with adding and subtracting is one, people forget to distribute that negative sign through the entire problem. That's an important step. The other problem people run into is when they see parentheses, they feel like we have to multiply. Parentheses do not mean multiply. Parentheses just means we have a group. Now, if there's nothing between the parentheses, then we multiply. But in these problems we saw there was a plus and a minus between, so we add and we subtract. Speaking of multiplication, though, how do we multiply complex numbers? Well, almost exactly the same as we multiplied real numbers. We treat the I like a variable. With one little exception, is that the definition of I squared, whenever we have I squared, that's equal to negative 1. So, going back to our radical examples, if we had the square root of negative 4 times the square root of negative 9, if we were to simplify this, the first radical, the square root of negative 4, the square root of 4 is 2, and the square root of the negative 1 is I. As we simplify the square root of negative 9, the square root of 9 is 3, and the square root of the negative 1 is I. So when we multiply these together, 2 times 3 is 6, and I times I is I squared. However, I squared is negative 1. Multiplying by negative 1 is going to change the sign on the problem, making it negative 6. 6 times negative 1. So that's the only change, is when we multiply by I squared, that's times negative 1. So if we have the square root of negative 6 times the square root of negative 5, we can simplify the square root of negative 6 by pulling the I out, root 6, and we can simplify the negative 5 by pulling the I out, root 5. And so when we multiply together, I times I is I squared. Square root of 6 times square root of 5 is square root of 30. But we also know that I squared is negative 1. So that's the same as saying negative square root of 30. Okay, let's drop the radicals and just start multiplying some complex numbers together. Let's start simple. Let's do 5i times 3i. We've actually already done this. 5 times 3 is 15. I times I is I squared. But I squared is negative 1. So that's 15 times negative 1 is negative 15. How about we do negative 2i times 4 plus 3i? Just like any other algebra problem you've seen before, if we've got something in front of the parentheses, we're going to distribute it through the parentheses. Negative 2 times 4 is negative 8i. Negative 2i times 3i is negative 6i squared. But again, when we see an I squared, that's negative 1. Negative 6 times negative 1 is positive 6. And we still have the minus 8i. I want to be careful here of another trap students run into, is when we start to see I squared equals negative 1, students often will start to make i's equal to negative 1. And i's are not negative 1. It must be squared to become negative 1. If it's just a regular I, leave it as a regular I. How about this one? 2 plus 3i times 5 minus 4i. You'll recognize that when we're multiplying two binomials, this time nothing between the parentheses, we FOIL. So 2 times 5 is 10. 2 times negative 4i is negative 8i. 3i times 5 is positive 15i. 3i times negative 4i is negative 12i squared. And again, we see that I squared is negative 1. So what we really have is 10 minus 8i plus 15i, and then negative 12 times negative 1 is positive 12. And actually, we're not done yet here because we can combine like terms. 10 plus 12 is 22, and negative 8i plus 15i is positive 7i. And we have our product. I want to notice what we've done in all these problems is we put the real part first and then the part with I second. That's going to generally be consistent. We like to put the real part first in our final answer. How about we do 3 plus 2i squared? Well, remember, squaring does not mean we square 3 and 2i and be done. That does not work, because there's a middle term that we have to worry about. So yes, to start off with, we do 3 squared is 9, but then the middle term is 3 times 2i is 6i. 2i times 3 is 6i, and 6 and 6 gives us 12 i's in the middle. Plus 2 times 2 is 4, and I times I, it's bad for it, and I times I is I squared. Again, we see the I squared. I squared is negative 1, so we have 9 plus 12i plus 4 times negative 1 is negative 4. So when we combine like terms, 9 minus 4 is 5, plus 12i. We now have squared this complex number. Here's an interesting one. 2 minus 7i times 2 plus 7i. If we try and FOIL this, I want to notice what happens, and you should be able to see this coming because of problems we've seen before. But 2 times 2 is 4. 2 times 7 is 14i. Negative 7i times 2 is negative 14i. And negative 7i times 7i is negative 49i squared. And why this is interesting is in the middle, 14i, I probably should get the plus in there. 14i minus 14i is 0. That middle stuff should subtract out. And we should have seen that coming by virtue of the conjugates that we were working with. We did this with radicals when we were rationalizing denominators, as we changed the plus and minus in the middle, and now we got rid of the radical in the denominator. Again, I squared is negative 1, so this is really 4 minus 49 times negative 1 is now a plus 49, which equals a final answer of 53. But the big one thing I want to notice here is 2 squared is 4, and 7 squared is 49. Normally with a difference of squares we had a minus in the middle, but with complex numbers there's a plus in the middle. We're adding the squares of the numbers, which leads to a nice general case. If we multiply a plus bi times a minus bi, a and b are the numbers we're working with. I is the square root of negative 1. When we multiply it out, first off, we know from our past experience that the middle stuff is going to subtract out to 0. So all we really need is a times a is a squared, and bi times negative bi is negative b squared I squared. But as has been the case this whole time, is I squared is negative 1. So we have a squared minus b squared times negative 1 is a positive b squared. So what we notice is if we are multiplying complex conjugates, we have a plus bi, a minus bi. One's positive, one's negative, and they're complex. They've got an I in there. We can just square both parts and add. And when I say parts, I mean the numbers, the a and the b. Or in example 7, it would have been the 2 and the 7. In example 2, we could have noticed this pattern sooner and said, well, 2 squared is 4, plus 7 squared is 49, and gotten straight to the answer. It only works with conjugates, but it's very important when we start talking about how we divide complex numbers. The whole idea behind dividing complex numbers and what we're going to do here is that we can have no square roots in the denominator. And remember, I is a square root. We don't like to have square roots. We don't like to have i's in the denominators. And so the way we fix it is the same way we fixed it with regular radicals. Notice again, I is no different than anything else. We multiply by the conjugate. And the nice part when multiplying by the conjugate, at least in the denominator, is we just have to square both numbers and add. So for example, if we have 2 minus 3i over 5 plus 4i, we don't like that I in the denominator, so we're going to multiply by its conjugate by changing the sign to 5 minus 4i in both numerator and denominator. Now we're going to have to work for the numerator. The numerator we actually have to FOIL out. No shortcuts. It's not a conjugate, so we have to go through all the FOILing. 2 times 5 is 10. 2 times negative 4i is negative 8i. Negative 3i times 5 is negative 15i. Negative 3i times negative 4i is positive 12i squared. All over. In the denominator, we're going to take our shortcut. We don't have to worry about the i's because we know we have to square both numbers and add. So 5 squared is 25. We know it's going to be a plus because they're complex conjugates. 4 squared is 16. Now again, I squared is negative 1. So I'm just going to fix right now. That negative 1 is going to change that plus into a minus. So now we can combine like terms. 10 minus 12 is negative 2. Negative 8i minus 15i is negative 23i. All over 25 plus 16 is 41. We can't factor and reduce, so this is our final solution. Let's try one last problem with division. 7 minus I over 3 minus 2i. Again, we don't like the I in the denominator, so we're going to multiply by its conjugate of 3 plus 2i. We'll do the same thing in the numerator, multiplying by 3 plus 2i. We simply change the sign in the middle of the denominator. And again, we will FOIL out the numerator. 7 times 3 is 21. 7 times 2i is positive 14i. Negative I times 3 is negative 3i. And negative I times 2i is negative 2i squared. All over the denominator's complex conjugates, so we can use our shortcut. 3 squared is 9, plus 2 squared is 4. Again, I squared is negative 1, so I'm going to cross that off and change the minus 2 to a plus 2. Because negative 2 times negative 1 is positive 2. And then we just have to combine like terms. 21 plus 2 is 23. 14i minus 3i is plus 11i. All over 9 plus 4 is 13. And we have our final solution. This is complex numbers. Not a unreal number, but it is the opposite of the real numbers. It boils down to we treat I as a regular variable, with the only exception that I squared is negative 1 to help us simplify expressions. Take a look at the homework where you will add, subtract, multiply, and divide complex numbers.